How's it going, everyone? Hope y'all are doing well. Had a good weekend. Pretty good. Yeah, it was relaxing. I did get some grading done, so it was somewhat productive. Not as much as I wanted to, but I'm okay with that. Oh no, well, we haven't done anything yet. Um, no, this is for my all of my other classes are basically taking tests right now. But I had two that took tests last week. I had to get graded. So. No, uh, I still I still haven't been able to contact Mrs. Knisley, so I haven't been able to give her the homework assignment for sections 2.1 and 2.2. What I may end up doing is I may just take a picture of the page and just upload it to Canvas and tell you which numbers to do. And I wish I could set up in my math lab though. Future value? Mm-hmm. So y'all are still in chapter 5? Yeah. Okay. So with future value, first of all, we have this formula. We have future value is equal to the payment times, and then in brackets here, 1 plus I, where I is the interest rate divided by a number of compoundings per year, raised to the n, which is the total number of compoundings, minus 1, and then divided by that I value once again. Okay. For example, you don't understand which formula when to use the right formula. Okay. Well, future value is used for investments, like when we're trying to save money for retirement, for instance. It's a future value. Whereas if we're trying to borrow money, then that usually is a present value problem. That's one way to think of it. So it's part of its context as far as whether we're saving money or borrowing money. Whether we're paying something off. That's a present value problem. Paying off a loan. If we have a sinking fund, or we're saving money for the future, or investing money, that tends to be a future value problem. Okay, this is problem 6 on page 247. We are saving, or we're investing in these different accounts. And number 6, we have a monthly payment of $900. And it's a 1.1% compounded monthly for 5 years. Generally, Brandon, yeah. So the first thing we want to do is, we already know the payment's $900. We really need to figure out what I and N are. Now for the I, this is basically the interest rate per period. Because when you have like a credit card that charges you 26% per year, they split that up over a 12-month period. So when it's 26% annual interest rate, they'll divide that by 12 because you pay monthly, and so it's whatever 26 divided by 12 is 2.1% every month. Okay. The same thing is true for future value. We take 1%. It's the annual interest in this case. Right. In that example, we would just divide it to get I would be equal to the interest rate divided by the number of payments per year. So we have 60 total payments, 5 years monthly. N equals 60, but R, 1.1% is 0.011, and M is 12 payments per year. Okay. So M and N are two different things. We want to make sure that we keep them straight. It's compounded monthly, so it's 12 monthly payments for 5 years, so 60 total payments. So I is equal to 0.011 divided by 12. Oh, is that it right there? Yeah. And then that's where it's that's one of the key details right there, is just distinguishing those two things, M and N. And so once we calculate I, then we can plug all these into our formula. So we take future value is our payment, $900. We have 1 plus 0.000917 raised to the 60th power minus 1 over 0.000917. And that should be adequate as far as approximating that number. If you look at the actual value of I, it's something like that. So I just made it 0.000917. Now when we enter that into the calculator, that's the other issue. So you can do it step by step, but if you want to do it all at once, well, mostly all at once, I would open two parentheses to 1.000917 raised to the 60th power, subtract 1, close the second parentheses, and then divide by 0.000917, and then multiply that by the payment 900 in front. And so this is the amount that we should have after the 5-year period. So 55,487 and 2 cents. 2 cents is important. Now we look at that and we say that's quite a lot of money. But remember, over those 60 months, we've been depositing $900 a month. So 60 times 900 is 54,000 right there. So we actually earned in that 5-year period $1,480, well, almost $1,500 in interest on top of the money that we deposited. So remember, it's not like $900 magically becomes $55,000. It's because we're putting that $900 every month into that account. That not only do we have our original $54,000, but we've actually gained interest over those 5 months, according to this interest rate. Now, 1.1% is not a huge interest rate. Generally, you see that for like a savings account, that kind of thing, where they're relatively low interest rate, but I don't know, it's better than nothing, I guess. But yeah. Anyway, any interest is good if you can get it. Okay. Were there other questions on future value? We can do some more if we need to, or present value, or anything else. What? Okay, yeah. Let me pull up your Canvas course so I can look at that. Yeah, absolutely. Hmm. Let's see. There we go. It's a problem 2 on the week 5 practice. I was scrolling here. Oh, I gotta sign in to Pearson. Okay, hang on. Okay, 1324. Nope. Sorry, guys, hang on. I had to sign in as your instructor, so. No, not your instructor, I mean the instructor for the other class. Alright. Jared, can you. I don't know. Can you just tell me what the problem. What that problem is you want me to work? That might be easier than me trying to find it. Yes, I would appreciate that because I'm having a hard time. Since I'm not connected to the your 1324 Canvas course, I'm not able to access through there. I have to go through everything in Pearson. Anyway, sorry about that. So while he's typing that, yeah, with the future value, the main thing is, and actually the main thing with all these things is once we establish which formula we're using, we correctly identify the numbers that we have to plug into each location. So to do one more like that, this is problem 8. Payment is $1,100, and it's made at in an account that earns 1.05% semi-annually. For 10 years. Okay. Semi-annually means how many times per year? Oh, still on page 247. Then after I finish this one, I'll answer Jarek's question. Semi-annually means how many deposits or how many payments are we making per year into this account. 2, good. Okay, 10 years. So 2 payments at 10 years means that N would be how many total payments are we making if we make 2 payments per year for 10 years? 20? Mm-hmm. And R is 1.05%. We'll make that 0.0105. So that identifies our main variables, R, M, and N. So we define I as R divided by M. So that'll be 0.0105 divided by 2. Which is going to be 0.00525. Okay, so our future values can be our payment, $1,100, times 1 plus I raised to the nth power minus 1 and then divided by I, like so. Okay. Now when we say 1 plus this, we can basically just say 1.00525. We don't really have to do that addition because we're just appending a decimal to a 1. So let's see. So we start off, we can do 1,100 times, open 2 parentheses, and we'll do, let's see, 1.00525 raised to the 20th minus 1, close 1 parentheses, and then divide by 0.00525, close the other parentheses, and that should give us our answer. This is 597, so we'll round that to 0.60. Now that's actually less than the last time, even though this is over a 10-year period, because in this case we're only depositing 2 times a year rather than 12 times a year, because the problem 6 we looked at was monthly. This one being semi-annually, we've only made 20 payments total of $1,100. Which means we've only deposited 22,000, but we did earn, over $1,100 in interest in that period. Okay. Are there any questions on number 6 or number 8 before we move on to Jarek's problem? That's a pretty involved problem there. Okay. Let's start with a fresh sheet of paper, I think, for that one. Alright, find the final amount in the retirement account in which the rate of return on the account and the regular contribution change over time. So we have 5 years we spend investing let's see, 4% monthly for 5 years. Oh, sorry, $365 per month at 4%. Yeah, in this case, because we're depositing money, this will be the future value. Yeah. This is actually 2 problems in one, though, because there's really 2 parts we're looking at here. After this initial 5 years, we then take that money and then deposit for another 5 years at $531 per month at 7% interest. $531 sounds like such a weird number to deposit every month, but not going to argue. Okay, so we have to figure out how much money is remaining after the first 5 years, and then we'll move on to the other 5 years. Okay, so for A, the future value, it is a future value problem. We know our payment, we said, was $365. 4% interest, so R is equal to 0.04. It's per month, so there's 12 months in a year. For 5 years means 60 total payments. Okay, 4% interest. This is compounded monthly, so M is 12. And monthly for 5 years is 60 total payments, or 60 total deposits. So I is equal to R divided by M, so 0.04 divided by 12. Which is 0.00, and then 3 is just repeating from there. I'll just put 4 down, and hopefully that's enough. So take our payment, and then in brackets we have 1 plus 0.003333 raised to the 60th power n minus 1, and that's divided by 0.003333. Okay. So our future value in this case, and this is just the future value of after the first 5 years that we're finding. So it's 1.003333 raised to the 60th minus 1, and then divided by 0.003333. So I got $24,198.88. Okay. So that's our future value after the first 5 years. So if after 5 years of depositing $365 every month at 4% interest, this is what we should have. Now, we want to find out what happens in the next 5 years after this. So ultimately, we're trying to find how much is present in the account after a 10-year period. Well, it looks like what we did is we took our money out of this investment and then put it into another investment after the first 5 years that we're putting more into it, and we're also getting a higher interest. Okay, so for B, we take this money and put it into the other account. Now, so we have one investment, or a one-time investment of $24,198.88 plus $531 per month for 5 years at 7% interest. Okay. So what's going to happen is this $24,000 is just deposited one time into this account that earns 7% interest. And that's over a period of 5 years. And interest is calculated every month. It's probably just a basic compound interest problem, because we're only making one investment, we're not making multiple investments. Okay? So it's actually two parts. We have to figure out how much money this earns as a single investment, one-time investment, and we have to calculate how much money this earns, and then put those two together is what it's going to amount to. So for the 24,000, 198.88. This is just our basic compound interest. And $531 per month. This will be calculated as a future value problem. Okay. because this is only a one-time investment, and it's just going to keep money according to how the account compounds every month for 5 years at 7%. So that'll just be a regular compound interest problem. Whereas this one, where it's a continuous investment every month of $531, that will be a future value problem. And then we'll do those two separate problems and add those numbers together, and that'll give us the total amount at the end. Does that make sense how we interpreted that? No? Okay. So whenever we do future value, the way that it works is that we're making payments every single month, or if it's monthly, or we're making every single quarter if it's quarterly, and so on. But a future value problem depends on making payments at every compounding cycle. Okay? And so $531 per month for 5 years at 7%, that's a future value problem. The other issue that we have in this particular example is that we're taking money earned from a previous investment and just throwing it into this account as a lump sum. So we start off with, so basically we're starting off this problem with this much money already invested in the account, and we're adding another $531 every month. Okay. Now this one-time payment, we're not making that payment every month. This is just from the upfront, initial deposit plus what happens every month thereafter. And so what happens is this money is still growing. We're just not adding to it every month. It compounds itself. So that 24,000 still earns interest, right? It's still going to earn interest every month because of the compound interest that's being applied. But we're not making other deposits on top of it. I mean, we're not repeating that investment every month because we only have that money one time. Okay, so it's still going to earn compound interest and still going to earn the same rate because they're all in the same investment. They're all in the same account. But this money will grow a little bit differently than how this one grows because this one's a repeated investment. Do we have a breakthrough there? Good. Anyone else still fuzzy or not quite sure? That remains to be seen what we need to do after we calculate this one. I think no, but maybe. Yeah, this is a very involved problem. For your sake, I hope it's not going to appear on the test. Yeah, and if this one, if you haven't talked about it already, it's the kind of thing that just sneaks up on you, and you're just not sure what to do with it. It's like, I mean, because I think probably everyone was okay doing the first part, getting that first future value part, because it's just a normal future value problem. The second part, though, is pretty involved, though. Yeah, ideally, you'll be able to just utilize the formula like we have been doing here today. So, all right, let me continue this on the next page. So, let's do the $24,198.88. Call it Part B1. Um, for 5 years, 7% compounded monthly. Which you can't see. There you go. Okay. So we back up a bit and we find our original compound interest formula, which I should know off the top of my head, but I don't want to give you wrong information. So the future value is equal to the present value times 1 plus I to the n. This is actually from, what was it from, Jarek? It was week 5 practice, I believe. Yeah, week 5 practice. So I think it's actually from my math lab. Okay. Hmm. Yeah, I don't know. I don't know. Well, I'll have to look, see if there's something in the textbook similar we could look at. Mm-hmm. Oh, well, maybe there isn't. So this is our interest rate, R over M, so it's 0.07 is our rate, 7%. It's compounded monthly, so there's 12 monthly compoundings, or 12 compoundings per year, sorry. So 0.07 divided by 12. So that'll be 0.005833. Okay, and then N, again, 5 years compounded monthly. So 60 compoundings. Okay. So the future value for this part oh, thank you, Geneva. That's good. This was right before where I was looking before. Or right below. Sorry. Anyway, continuing on this example, so we have our $24,198.88, and then 1 plus I is 5833 raised to the 60. Now again, we do the number raised to the exponent first, and our multiplication is last on our order of operations. So let's take 1.005833, raise that to the 60th power, then take that answer and multiply it by 24,198.88. So after another 5 years, our $24,200 will grow to $34,304.26. Which is pretty significant, but it is a 7% interest, so it's understandable that it grew quite a bit in that time period. Alright, so I guess we can call that future value number 1. Now, the other half of this problem is that we still have this other $531 per month at 7% for 5 years. Okay. So our payment is $531. Now, we'll actually end up using the same I value, 7% per month, or monthly compounding, so 0.07 over 12. So I is R over M equals 0.07 over 12. 0.005833, and we'll still use n equals 60 compoundings. So I and n are identical for both parts of the problem. It's just a question of whether we have one initial deposit or we have a deposit every single month. And that's what's going to change the calculation there. So in this case, future value is the monthly payment times 1 plus I to the n minus 1 over I. So future value 2 in this case. Do you see now what you're doing, Brandon? 531, 1.005833. Cool. 60 minus 1 over 0.005833. And we see that because of the different formulas that we're using here and here, we are going to get a little bit different value for this. So we'll take 1.005833, raise it to the 60th power, subtract 1, divide it by 0.005833, and finally multiply by 531. So we get $38,015.44. So now we're going to add the two future values together, and we should get the total amount remaining in the account after the end of the second 5-year period. So FV1 was $34,304.26. Here we got $38,015.44. If we add those together, no, we're still trying to find the total amount left after 1 year. So $72,319.70. Yeah, this problem we don't end up subtracting anything unless we want to find the actual interest earned. That's the time when we would subtract, is if we want to calculate the interest that was actually earned. And that may come in the next part when they want us to find the we're $1 off. I'll take $1 off. Probably that's just rounding errors. The other question though is oh, never mind. That is the question. So we're okay. Yeah, the problem will specify if we want to find the interest earned versus the total amount. So yeah, it says 72,321. So we're off by $1.30. I feel we'll be okay for missing $1.30. And exactly what it was is the rounding, because I stopped rounding after 6 decimal places, or I rounded after 6 decimal places on the I. And so if we took that further, that would give us a slightly higher value. Yeah, because that would be more decimal places. And with a slightly higher I value, that would increase the number for both of them. Yeah, and so if we wanted to be real specific, we could just, and this is a repeating decimal, this 3, so I mean, really we could just enter in as many 3s as we can enter into our calculator, and that should give us a better number. Yeah. I gotcha. Yeah. Yeah, but like you said, the main thing is the the process, really. Rounding is something we can work on, but as long as we got the process down, that's the big deal. Yeah, so we had different. Going back to the start of the problem, we began with 2 different scenarios. Basically, for 5 years, we had one investment amount at one rate, and then for another 5 years, we took that money and invested it in this account, and also paid more every month at a newer, higher interest rate. This is for what y'all would have to do in this particular chapter. I don't know if it gets much more difficult than that. You know? Yeah, I mean, I guess they could have you make an amortization schedule in Excel. That would be interesting. But as long as you know how to use Excel, that's not terrible. Yeah, and that's the issue with online homework, is that making sure you follow not only the steps of the problem, but also how they want it entered, yeah, sometimes that makes it a bit of a challenge too. So just to kind of go over what we did one more time. We had two parts to this problem. Basically, one 5-year investment where it was $365 deposit every month, earning 4% interest in the account. And after that 5 years, we took that money and invested into another account for 5 years where we also deposited another $531 per month. Again, this earning a 7% interest. So the first part of the problem is a very straightforward future value problem. We had a payment of $365, interest is 4%, so R equals 0.04. It's 12 months, so M is 12, and 12 months a year for 5 years was 60 total payments, 60 total deposits that would make into this account. We calculate I equals R divided by M, and again we rounded there, so that also leads to the rounding error that's present in this problem. But as you can see, that had a cumulative effect of $1.30, so not huge. That's why I went to 6 decimal places. Apparently they want us to go to as far as we could possibly go in our calculators, which is, it's not going to change it by too much, like we said. Anyway, we get our I value, plug it in here and here, N is right here, and then just calculate everything and multiply by 365. And we came up with the value of $24,198.88. I'm rounding to the nearest penny at this stage. Now, I mean that's the, like I said, that's the quote-unquote easy part. That's the future value part, and that just follows a normal future value problem. And that was for the first 5-year period. Now the issue is we took this money, we invested it into another account, and this one earning 7% interest every month, or and on a monthly basis. Not 7% every month, because we divide the 7% by 12. And then we're also paying another $531 every month into this account. So probably what this means happened is that over that first 5 years we increased our credit rating, and we also were doing a little bit better financially, so we were able to put a little bit more away, and we're able to invest in a higher interest account for whatever reason. So anyway, so now we had this much money at first, and so we have a one-time investment of that amount we had at the end of the first 5 years, and then we're going to invest another $531 every month following that for 5 more years, and they're still earning and we're earning 7% interest. So our one-time investment of $24,198.88 is basically a compound interest problem, whereas the monthly investment of $531 over that 5-year period is a future value problem. So we split up into 2 parts at this point. I called it B1 and B2. So for B1, we just made a one-time deposit, but it stays in this account for 5 years, earning 7% compounded every month. And so the future value in this case is just the present value, the initial investment, times 1 plus I to the nth power. That's our compound interest formula. I and N are actually identical for both parts, because R divided by M is 0.07 over 12. Get that value. And it's for 60 more compounding, 5 years, 12 times per year. And so there's 60 total compounds that are applied. So we plug it into the formula and we get an ending value of $34,304.26. Now, that's not the only thing that's in the account though, because we're also making at the same time a monthly deposit of $531 into the same account. Now, that's our payment, $531. This is a future value problem with a regular payment versus a one-time payment. So we use our future value formula from section 3. This part was section 2. This part was section 3 of chapter 5. We have $531. I is still 0.07 over 12. N is still 60, same as B1. But now we have a different formula for future value in this case. It's payment times 1 plus I to the n minus 1 over I. We get everything plugged in and calculated. And that's what we have after 5 years for the monthly deposit that we're making. $38,015.44. And so we add that to the money that we had from our one-time investment being compounded for 5 years, which gave us an ending account total of $72,319.70. Again, a little off from the answer that Pearson had, but when they say 72,321, I feel like we're close enough that we're okay. At this point, you can just chalk it up to rounding error. And we did round 2 different times in that process, and that's probably what led us to being off by that $1.30, or give or take. But yeah, that's the main thing here is being able to go through each of these steps and arrive at that conclusion. Alright, so that was a pretty crazy problem, though. And it's unfortunate you hadn't seen an example like that before you're expected to work it, because that's not something we really expect you to have the understanding for just yet, just going over the homework problems like we have been in the class. So. Sure. So we have the ending value, but we need to find the payment. Okay. I'm looking in the wrong section. Hang on. All these problems were not what we were looking for. Okay, 5.3. I'm sorry. Okay, here we go. Oh, sorry. Yeah, that and what you're talking about now, Jarek, is what's called a sinking fund problem. Is that we know how much money we want after a certain time period. We just have to know how much we need to deposit into a particular account to achieve that goal. Let's look at what would you do fractions of a year? Anyway, let's look at 16. This is someone else's textbook. I don't know why 15 is circled, but 16 we want to have $25,000, and the money earns 9% compounded quarterly for 3 1/2 years. So this is on page 247, number 16. So our future value is 25,000. And we have 9% compounded quarterly. for 3.5 years. Okay. Now, first of all, the 9% compounded quarterly, that means R is 0.09. M, if it's quarterly, that's 4 times per year. And for 3.5 years, N is equal to 3.5 years times 4 times M, basically. 4 times per year. So N is equal to, what is that? Let's see, 14 payments? Or 14, yeah, 14 payments. Okay. And so the idea here is we're still using the same formula. Well, we could use the same formula. Okay. What we do instead is we turn this formula around. So basically we have future value equals payment times a fraction. What happens if we want to take this fraction and move it to the opposite side? Like, payment will equal future value times what? Well, what ends up happening is whatever this fraction is on this side, if we want to move it to the other side, we basically have to divide it. We have to take future value divided by this expression to get payment by itself. But if we're dividing by a fraction, it's the same thing as multiplying by the reciprocal. So if we want to rewrite that equation, we could, and we can just say payment is equal to the future value times I over 1 plus I to the n minus 1. It's not strictly necessary to do this, because what we can do is we can plug in the future value. We can actually calculate this with the information that we have here. And once we calculate this, we'll say, okay, future value equals payment times that. That means we have to divide that number over here and to get payment by itself. So whether we use a formula to do it or we just use kind of a common sense approach, we should end up with the same outcome either way. But if you want a formula for it, it would look like this. Alright, so our future value we know is 25,000. Now I, in this case, is R divided by M. So 0.09 divided by 4. So that's 0.0225. There we go. So 0.0225 over 1.0225 to the 14th power minus 1, close parentheses. This is actually a lot harder to do on the calculator, so you may want to use this formula instead. And then just calculate this value, we know what that value is, and just divide them together afterwards. Using this pattern is a little more involved, so maybe I would recommend the other instead. So we could do that in a calculator, or let me just show you the alternative because I think it'll be easier for us. Let's say future value is payment means 1 plus I to the n minus 1 over I. We know future value is 25,000. Payment is unknown, but we have 1 plus point, or no, we could just say 1.0225 to the 14th minus 1 over 0.0225. So we'll go ahead and calculate this value here. So 1.0225, raise it to the 14th power, enter, subtract 1, enter, and then divide by 0.0225, enter. So we get a value here of 16.243708. So I'll round a little bit. I again went to 6 decimal places. I guess I like that for some reason. And then the payment will be 25,000 divided by that number. Now, the one way we can use our calculator to not round is we can use this answer function. And that would give us 1539.06 if we round. So as long as we made that monthly payment, then we should expect to have 25,000 at the end of that 14 payments after 3.5 years. Does that make sense? Good, good. And I said you could do it this way or this way. You might actually find this way easier, so if you wanted to do that, that's fine. From a calculator standpoint, this is a lot easier than this, personally speaking. So. When this term is in the denominator like this more complicated terms in the denominator, we actually have to use a lot of parentheses to actually do that properly in the calculator. So, whereas as you saw me do, I could do this step by step in the calculator. Do this part to a power, enter, subtract 1, enter, and then divide and enter and get to a result here. So from a calculation standpoint, I think it's easier just to use our same formula, but solve for the payment at the last step. Okay. Other questions that we wanted to go over? Okay. Have you all gotten into present value yet in section 5.4? Or is 5.3 kind of where you're at the moment? So yes, you've done a little. Okay. Let me. Brandon, you were asking specifically, do problems get any harder than that? And I happen to notice some at the end of 5.4, and I would say these are a little bit more difficult than the one we were doing right there. And the idea is that in these retirement planning problems, you contribute a certain amount each month for at a percent rate, at a compounded at a certain period for some number of years. So you do a future value problem, and then after that, you want to make monthly withdrawals for another 30 years. Okay, and so it's like a future value problem, and then it's a present value problem on top of that. So those can get a little hairy as far as the work that's being done, but I don't think it's any worse than the one that we did. It could be in some cases, just depends. I remember when I last taught this; those were pretty crazy. So it's been a good 5, 6 years since I taught this. Okay. If I have anything for that y'all can use. I'm gonna look real quick in my Canvas. Let's see. This would be business math. Hmm. Well, apparently I haven't taught it in the past 6 years because it's not in my old Canvas courses. Not since fall of 2013 at least. So, hmm. Oh well. I had an interesting document we might be able to use here, but I don't have it handy. I'll see if I can find it. I don't have access to my work computer right now, unfortunately, because I know it's there, but I may have it here somewhere. It's about future value and present value, but I think it was a pretty helpful one. But if I have it, I'll upload it for y'all. Anyway, I think it was about making doing amortization specifically. All right. Did y'all have any questions on 2.1 or 2.2? I haven't made a formal assignment on that, so I do apologize because I said I would. And I will, but I haven't yet, unfortunately. Okay. All right. You know what? Why don't we just stop there today? Yeah, probably tomorrow you're going to be working on 5.4, I would bet, if you've already done all of that stuff in 5.3 we talked about. She may do some of that. She may do a problem like what we did today with the at the end of 5.3 with the compound problem with the future value problem. But otherwise, I guess she'll be doing 5.4. Yeah. Anyway, so we'll go ahead and stop there today. But y'all let me know if you do have questions, and I'll try to get that homework set up. Um, but y'all take care, and we'll meet again on Wednesday. So have a good day.